Hey guys, welcome back. This is our last section to 2.1. In this section, I'm going to talk to you about partitioned matrices, linear combination, which is the fundamental theme of linear algebra. Okay, so we're going to run through this. A x equals b can be represented in a more convenient way by partitioning the matrices a and x in the manner below. So A is the list of coefficients, X is our variables, okay? And then B is our constants or our solutions, okay? So let A be the coefficients, X be the column vector, do you remember that, of unknowns, and B be the constants. Then we have our coefficients, which is A, our column vector, which is X, is equal to B. And I should probably bold this to show you that it's a column vector. So what we have really going on here is what we did in our previous video with matrix multiplication, right? It's like A11 times X1, A12 times X2, right? We go across this way and down here, and that's going to equal to the B, okay? Great. What we can do here is we can take the column of the coefficients, A11, A21, and so on, and A21, A22, and so on, and take our unknowns and write it this way, so that A times X is equal to X1, A1, X2, A2, and so on. What I want you to realize in this case is that A1 is the entire column, A2 is the entire column, right? So if we take all of the columns times X1, X2, and so on, we get B. So A1, A2 are the columns of matrix A. So what we just did here was basically take a look at this. We partitioned it, we broke it into pieces, and this is called a linear combination of the column matrices. Linear combination of the column matrices or the column vectors, okay, is the heart of linear algebra. So in general, like a theorem, the matrix product AX is a linear combination of the column vectors A1, A2, A3. Remember, this is A1, this is A2, this is A3. We're representing it as A1, A2, A3, right? It's not A11, A21, right? It's A1, A2, the first column, the second column, and so on. Furthermore, the system AX equals B is consistent, which means it has a solution if and only if B can be expressed as such a linear combination, where the coefficients of the linear combination are a solution to the system. So here, I have this example that has 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And I'm rewriting it in terms of a partitioned matrices. So I'm putting 1, 4, 7, 2, 5, 8, 3, 6, 9, x1, x2, x3, and that's going to equal to, I should put the vector here, okay, 0, 3, 6. I used reduced row echelon form, and I reduced it down to here. I notice that I have one row that's all zeros, which means I have infinitely many solutions. So I can pick any solution based off of what I did there. So x1 is 1, x2 is 1, x3 is -1 based off of our parametric representation, right? And so what I'm going to do here is I'm going to go back to this, x1, x2, x3, and I'm putting those numbers here. And if you look at this, 1, right, plus 2 is 3, minus 3 makes 0. 1 times 4 plus 1 times 5, right, minus 1 times 6 makes 3, and so on. So that's one of our solutions. That is, B can be expressed as a linear combination of the columns of A. So this is one of the ways that we can express B as a linear combination of the columns of A, okay? Just as you partitioned A into the columns and X into the rows, it is often useful to consider M by N matrix partitioned into smaller pieces. So let's pretend that I gave you this matrix. You can partition it however you want it. You can go like this, and you can have like this quadrant, this quadrant, this quadrant, this quadrant. Even though these two are not the same, it's still fine. You can do all columns, and I'll represent as C1, C2, C3, C4. Notice the way that I wrote this is because I would put C1, C2, C3, C4 going across. You can also do rows if you want, okay? Notice how I did the rows going down. So you can do any of those, okay? So I'm gonna leave you with that's pretty much it. Many real-life applications of linear systems involve enormous numbers of equations and variables. For example, a flight crew scheduling problem for American Airlines required the manipulation of a matrix with 837 rows and more than 12,750,000 columns. To solve this application of linear programming, researchers partitioned the problem into smaller pieces and solved it on the computer. So that's a source called Very Large Scale Linear Programming. It's a case study in combining interior point and simplex methods, okay? So there are many applications where you are going to want to divide these up and write them into linear combination. So for just this section, I wanted to end with how to do that. So once again, we will leave with this here, okay? This is a linear combination of the columns of A. I hope you have a great day.